Welcome to Physics 2211, Lab 1, Constant Velocity. The goal of this lab was to find a constant velocity of an object. In this case, a lacrosse ball was used. The results of the lab were determined by using both an experimental and a computational model. The different principles of physics used was Newton's first law, which states an object in rest must stay in rest, and an object in motion must stay in motion unless acted on by an outside force. This is important to the lab because if this is true, the net force must equal zero. Newton's second law, which states that force is equal to mass times acceleration, is important because an object has a constant velocity, then the net force must equal zero. The momentum principle, which is related to Newton's second law, was an important factor as well, because if there was a change in momentum, that would mean a force was acting. The formulas and calculations used. Newton's second law was used, which is force equals mass times acceleration. This is the same thing as change in velocity over change in time equals net force over mass. The velocity update formula can be found from this, which is final velocity equals initial velocity plus net force over mass times change in time. If net force is zero, then final velocity should equal initial velocity. The position update formula can also be found from this, which is final position equals initial position plus average velocity times change in time. The momentum principle was another formula used, which is final momentum equals initial momentum plus net force times change in time. The momentum formula is just momentum equals mass times velocity. Both of these two combined give us this. The initial position from tracker was 0.001. The average velocity equation can be used to find the initial velocity because our velocity is constant throughout, and that gives us a velocity of 0.988. As you can see here in tracker, the ball was used as a measurement of length, which is a reference for the rest of the system. You can also see that the origin of the axis was placed at the center of the ball. When the video is played, it does not start at the very beginning of its movement. This is to account for the initial acceleration that is occurred on by the ball. It also does not go to the very end of its movement when the ball would be decelerating. In this experiment, the ball is the system and the ground and everything else is the surroundings. As you can see when you look at the table, the time has a time step of 0.033, and you can also see the positions. When you look at the graph, you can see that it has a positive slope in the x direction. Therefore, the ball also appears to have a consistent slope, which would infer that the ball has a constant velocity. Here in GlowScript, you can see this code creates a visualization of the ball. This creates the graphs and the tables. The ball's mass is here, which was found for triple beam balance. The initial position was found from tracker. The ball's initial velocity was found for points in tracker. The start time is 0, a time step of 0.01. A while loop was used to repeat the below code until the time 0.667. The net force was 0 because we're solving for constant velocity. The velocity update formula is here. The position update formula is here. A print statement here puts the time in the x-axis and the position in the y-axis. As you can see, the ball here follows a similar path to the ball in the tracker video. And you can also see that the velocity has a similar path to the same graph. Now that we have looked at both models, let's look at a comparison between the two graphs. Here are the times, here are the positions from tracker, and here are the positions from the computational model. As you can see, the graph is very similar at the very beginning, however there's slight variation towards the top part. We will talk about this variation on the next slide. Given those graphs, we can make these observations. The ball's velocity stayed constant throughout. The net force on the ball was 0 because the normal force and the force of gravity, as well as any other forces, canceled out. There are very few variants between the two graphs, which is not enough to disprove Newton's first and second laws. The slight variation between the two models could be a result of minimum error, such as a slightly warped floor causing an additional acceleration in the middle of the experiment, or the position of the tracker points not being exactly at the center as a result of human error or the blurriness in the video. What if I made the choice to orient the axis in the positive x direction? This way I would be dealing with positive numbers and a positive slope. If it was in the negative x direction, it would be very similar results. However, the positions would be negative, and the graph would have a negative slope. What does it mean? It is not possible to know how many pushes and pulls were acting on the system to give a net force of 0. The reason because of this is that most things are actually applying a force to the object. However, most of them are too small and are canceled out, which means they have no impact. What we do know is that our object had a constant velocity, which means the net force of the system must be 0.